right, here we are going to solve the week 11 Wednesday pre-class problems. So I posted the problems and then the answer key, and now here I'm going to go through and solve them for you so we can go through and do the full mechanisms for the reactions. So in this case, first up, we have this complex cyclohexane ring, and we're going to react it with sulfuric acid and heat. I want to talk a little bit about sulfuric acid because you're going to see me use it with relative frequency. So this is really what sulfuric acid looks like. And sulfuric acid is a really good acid because it's completely non-nucleophilic, even when you look at its conjugate base. So unlike hydrochloric acid, so hydrochloric acid, for example, after it donates its proton away and it forms its conjugate is chloride. Chloride is nucleophilic. So we've had that chloride ion act as a nucleophile in some reactions. Sometimes, in particular when we're reacting with alcohols, we don't want to have a nucleophilic conjugate. So if we were to remove a proton from this, oh my goodness, there we go. If we were to remove a proton from sulfuric acid, this is what the conjugate looks like. So this is the conjugate base of sulfuric acid. Conjugate is with the proton removed. And this is completely non-nucleophilic. So if I were in class with you right now, I would be like, well, why? Why is this conjugate base non-nucleophilic? And you would all think about it for a while before maybe one of you says resonance. And that is the right answer. This has a lot of resonance structures. So one of the possible resonance structures for this conjugate base looks like this, where we can resonate that negative charge into those other oxygen atoms. Resonance lowers the nucleophilicity because that negative charge is smeared out amongst all three of these oxygen atoms. It's not just completely localized on that oxygen, so it's non-nucleophilic because it's not a really concentrated negative charge. It's also non-nucleophilic because this is really bulky. So bulky things aren't usually good nucleophiles. They can't get into bond. So sulfuric acid is used as a non-nucleophilic acid. Let me try to erase all this stuff now. Give me some more room to work on the actual problem here. So we have this alcohol, and we're going to react it with sulfuric acid, and then we're going to heat it. So the first step of the mechanism, and again, hopefully you guys are getting used to this by now, the acid protonates the alcohol. So we form a really good leaving group, which is water. This chiral center hasn't been touched, so we're not going to worry about it. That chiral center hasn't been touched, so we're not going to worry about it either. This technically is still coming out at us. Now we have to look and see what's going to happen next. I haven't given you a solvent here, but water is a really good nucleophile, and this is a secondary carbon atom. So what's going to happen now is the leaving group is just going to leave. This ends up being like an E1 mechanism. So we form the carbocation. I haven't even really cared about the stereochemistry. I haven't really had to draw this in chair conformers because when you have an E1 mechanism that takes place on the carbocation, it doesn't matter about the anti-periplanar arrangement. Either one of these beta hydrogens is equally likely to be removed. So we're going to remove the beta hydrogen in this case. Oh, and then you're going to ask me, well, what base do we use to remove it? I like to use water as a base. Water is almost always present when you have sulfuric acid. We also formed water here as the leaving group. So this is going to come through and eliminate it. We knew it was elimination also because heat was added. So that beta hydrogen removal will lead to this alkene. This stereocenter wasn't touched, so it remains the same. This stereocenter wasn't touched, so it remains the same. We also, let me see if this will give me a different color here. Oh, that's way too light. We can't see that. Okay, I'm just going to have to do that in black then. This beta hydrogen here can also be equally likely as removed. So there's no real difference between removing this guy or removing this guy. So if we remove this beta hydrogen, we're going to form the double bond here. So removal of that beta hydrogen leads to that alkene. So now if we look at the stability between these two, try to predict which one is going to be formed in higher quantities. This one is di-substituted. This one is also di-substituted. So since they have the same amount of stability, they're going to be formed in a 1-to-1 mixture. All right, next up we have this alcohol, and we're going to react it with hydrobromic acid. So again, I want you guys to become automatic with this. Alcohol sees acid and gets protonated. That turns the hydroxide into a very, very good leaving group of water. Now again, I haven't given you a solvent. Oh, I'm going to just show you the bromide is also formed. I haven't given you a solvent, but acids really, you can't have an acid except if it were in a protic solvent, number one. Number two, we've turned this into such a good leaving group, and it's on a secondary carbon, that the leaving group is simply going to leave. That forms the carbocation intermediate. Now, we've got to be careful here. Remember the things a carbocation can do. React with a nucleophile, eliminate a beta hydrogen, resonate, and rearrange. So be careful about that rearrange. Every time you get a carbocation, you need to analyze it to see if it's going to rearrange. If a carbocation can rearrange to become more stable, it will. So in this case, we can see this is a secondary carbocation. If it just switches places over here, it's going to become tertiary. So this carbocation undergoes a 1,2 hydrogen shift to rearrange to form the tertiary carbocation. That's more stable, and so we're going to fall into this tertiary carbocation. Now we look to see what this carbocation can do. React with a nucleophile, eliminate a beta hydrogen, resonate, or rearrange. Heat was not added, so it's going to react with a nucleophile. The nucleophile it will react with is that bromide. So the product of this is this. There you go. Next up, we have another alcohol reacting with non-nucleophilic acid, sulfuric acid, and we're going to heat it. Alcohol sees acid and gets protonated. Automatic, hopefully by now. That transforms the hydroxide into good leaving group water. Again, I haven't told you that it's in water, but you can't have sulfuric acid without water present. And it's on a tertiary position. Leaving group leaves. We form the tertiary carbocation. So things a carbocation can do: react with a nucleophile, eliminate a beta hydrogen, resonate, rearrange. This is not going to rearrange because it's tertiary. So since it's already the most stable it can get, then it's going to stay that way. Now we look to see, is it going to react with a nucleophile or is it going to eliminate? I've told you that heat is added. Since heat is added, it's going to eliminate a beta hydrogen. So I'm going to show water here as the base that's going to eliminate the beta hydrogen. We have two different sets. We have beta hydrogens here and here. If we eliminated one of those, we would form a di-substituted alkene. So if we eliminate this beta hydrogen, we form, oh, that arrow is terrible, just so you guys know, that's a terrible arrow. Let me draw it better. This is pulling off the proton. Then the electrons that were in this bond swing down to make the alkene. So the product that's formed is a tri-substituted alkene. All right, so that was all alcohols reacting with acids, but remember, alcohols are amphoteric. They can react as acids or they can react as bases depending on what they're put with. This compound here is called sodium amide. Sodium is a positive charge. That means that this NH2 is negatively charged. This is a really, really strong base. Just like sodium hydride is a strong base, sodium amide is a really, really, really strong base. So we're putting our alcohol in the presence of a really, really strong base. That means that the alcohol is going to get deprotonated. The base pulls off the proton. The electrons that were there on between the oxygen and the hydrogen get localized on the oxygen. This turns this into an alkoxide. Alcohols react with strong bases to become alkoxides. Now we have a nucleophile and a leaving group in the same molecule. So the nucleophile comes in, pushes the leaving group away. This is one of those intramolecular reactions. So figuring out what size ring we have, we're going to have a 6-membered ring with the first member being oxygen. So oxygen is bonded to 1, I'm sorry, this is 1, to 2, 3, 4, 5, and 6. And we have a methyl group at carbon number 6. So this guy here that's kind of floating off on its own, that's coming off of here at carbon number 6. Next up, we have a halohydron. A halohydron is when you have an alcohol right next door to a good leaving group. In this case, it's a bromide, a halogen, really. So the halo is the bromide, the hydron is the alcohol. So that's what a halohydron is. We're going to react it with sodium hydride. Sodium hydride is a really, really strong base. Alcohols react with strong bases to become deprotonated. So again, we're going to pull off the proton. The electrons that were in the bond between the oxygen and the hydrogen get localized on the oxygen. We form an alkoxide. Now we're set up again for an intramolecular reaction. We have a good nucleophile in the same molecule that we have a good leaving group. So in this case, the alkoxide comes over and pushes the leaving group away. The product of this reaction is an epoxide. An epoxide is a 3-membered ring in which one of the members is an oxygen. So this like triangle where one of them is an oxygen is an epoxide. This is the epoxide that's formed when the alcohol is deprotonated and pushes the bromide away. So now we have this reaction of POCl3. And again, you don't need to know the mechanism for this reaction. The formation of the product between the alcohol and the POCl3. It does not matter to me that you know. What it does matter to me is that these reagents do an E2 elimination on alcohols. And the reason why E2 is important is because you get absolutely no carbocation rearrangements. You get no carbocation rearrangements because no carbocation is formed, because it goes E2. So really, the way you can see this, I'm never going to ask you for a mechanism. You know that this alcohol isn't going to go anywhere. So we're going to see, we know that that's going to get pushed out. That's the leaving group. We got to eliminate a beta hydrogen. There's no beta hydrogens at this location. So what's really going to happen is that beta hydrogen is going to get removed. Some random base will come through, remove that, form the alkene, push the leaving group away. This is not the full mechanism, I promise. There's much more complicated stuff that happens between the alcohol and the POCl3 first, but I'm never going to ask you for the mechanism of this reaction. You just need to know what the reagents do. The reagents perform an E2 elimination with secondary alcohols so that no rearrangements can occur. So then the product is this alkene, and those methyl groups stay there. That's completely different from what happens when you react this same molecule with hydrochloric acid and heat. So, first step, alcohol sees acid, alcohol gets protonated. That transforms the hydroxide into very good leaving group water. Very good leaving group leaves. We form the carbocation. Things carbocations can do: react with a nucleophile, eliminate a beta hydrogen, resonate, rearrange. This is a secondary carbocation. If we could get it to switch places up here, one of the methyl groups moves, it can become tertiary. This is a 1,2 methyl migration. The methyl group moves over. So you can think about it as the methyl group and the carbocation change places. So this secondary carbocation rearranged to form the tertiary, which is more stable. Now we have heat added, and so thusly we're going to do an elimination reaction. I like water as my base that will do the elimination. We formed water here. So we look around for beta hydrogens. The beta hydrogen over here, if we form the alkene, would be 1, 2, 3, tri-substituted. If we eliminated a beta hydrogen here, it would be di-substituted. If we eliminate the beta hydrogen right here, it would be tetra-substituted. Zaitsev tells us that we're going to eliminate the one that leads to the most stable alkene. The most stable alkene is tetra-substituted. So the product of this reaction is that. It comes about from the carbocation rearranging. Last but not least, we have a retrosynthesis problem where we're going to synthesize this alkene from an alcohol, and there's lots and lots and lots of ways that you can do this. But taking it one step backwards, we know that when you form alkenes, you eliminate a beta hydrogen and a leaving group. So we could have like a leaving group here and then the beta hydrogen here. It's also equal possibility that if we put the beta hydrogen here and the leaving group here, those both work because Zaitsev tells us we're gonna form the most stable double bond. So either one is gonna form the alkene there. So now we know kind of what the alcohol is gonna look like. If we put the alcohol there, we're gonna react it with an acid to make it into the good leaving group and heat. That'll do the elimination. Or we could put it here and same kind of conditions. A strong acid to transform the hydroxide into a good leaving group, and heat will also cause that elimination to occur.